Morning geometry classes. We are going to take a look today at lesson 11.4b, where we're going to calculate probability through a geometric lens. So we're going to use our geometry, determine the likelihood of particular events happening. So we're going to take a look at two key concepts. One that will deal with probability when we're looking at a number line, and then we'll also look at probability dealing with area. So key concept number one, probability and length. So we need to recall as background information the information I have in thinking bubbles, that the probability of an event occurring is always the ratio of favorable outcomes, those that you are looking to happen, over total possible outcomes, all the different ways that it could come out, not necessarily just the outcomes you are looking for. So for our number line here, we're looking to figure out what is the likelihood or probability that a random point will land in the blue section here on our number line, CD. What is the likelihood of a random point happening somewhere in this segment when the point could be anywhere on this segment from A to B? So to figure out whether or not any random point K is on CD, we would have to figure out how long it is from C to D. And then we would also have to know how long it is from A to B, and we'd have to write the ratio of the length of CD over the length of AB. That would give you the likelihood or the chances of a random point being selected on CD. What about if we're dealing with areas rather than just segments on a number line? Well, again, the probability concept is the same. So the probability of an event occurring is the ratio of favorable outcomes where you want it to be over total possible outcomes where it could be. So in the case of this diagram here, if we are saying what's the chances that a random point is selected that happens to fall in this red section labeled M, when a random point could be picked anywhere out of this entire figure, all of the blue area and the red area together. Well, the probability would be the area of M, this smaller area, out of the entire area, all of the blue and the red area together. That's the area of J. And that would give you the probability then of randomly picking a point in the red area when it could land anywhere in all of the blue and red area together. So let's put this into action now. Guided practice 1 through 3. We'll have you practice with figuring out the probability of a point being chosen at random on a number line. And then you're looking to see in a particular area of the number line where you want the point to be, what would the likelihood of it actually being there when the random point could be picked from a larger segment of that number line. So guided practice 1 through 3 will refer back to this particular number line here labeled as you see. We're going to write our answers for our probabilities in fraction, decimal, or percent form, because remember, fractions, decimals, and percents can all express the same value, and so we're going to make sure we understand that we can report our probability answers in any one of those forms. So question number 1, what is the probability? This is how we write probability. We put a letter P, and then we enclose in parentheses what we want to have happen. What is the probability of a point on RT, that is, that we're going to get a random point somewhere in between -2 and -1 out of all of the possible places where it could land from -5 to 5, because that is the segment PQ. What's the chances of randomly selecting a point between R and T when you could randomly select a point out of all of the locations on the number line from P to Q, from -5 to 5? Well, to figure that out, we're going to first calculate how long it is from R to T. Okay, and to find out how far it is from R to T, we're going to take the absolute value of the difference of those two numbers to see how far it is. Well, we can kind of see that it's one space from -2 to -1, but using our absolute value difference, we can get that officially by subtracting -1 minus -2 and taking the absolute value.
Or we can subtract it the other way, -2 minus -1. And we take the absolute value of that, we would also get 1. So it doesn't matter what order you subtract these in because you're taking the absolute value when you're done. So there's one space here out of, well, how many total spaces could your point be chosen from -5 to 5? Again, we will take the difference of those 2 points, either 5 minus -5, take the absolute value of that, or subtract these in the other order, and you would get -10 inside the absolute value bars, which would return an absolute value of 10. So there's one chance out of 10 that you would actually randomly pick a point here, because there's one space here out of a total of 10 spaces altogether. 1/10 is the same thing as the decimal 0.1, which is the same thing as 10%. So that gives you the 3 different forms to report your answer for the probability of picking a random point that would land right here between R and T, when it's possible to pick a point anywhere from -5 to +5. 1 out of 10 chances. Guided practice 2 refers back to that same number line, but this time we're trying to find out what are the chances, what is the probability of picking a point on segment TS when we're still limited to picking a point on line segment PQ. Well, again, you find how far it is from T to S. So from T to S here, from -1 to 4, you find the difference between those two numbers. It doesn't matter what order you subtract those two numbers in, as long as you take the absolute value, you will get 5. So I chose to subtract it 4 minus -1. I could have also subtracted it -1 minus 4. As long as I take the absolute value, I will get 5. And then my denominator is going to be the same as my first problem because I'm still limiting myself to picking a point somewhere between -5 and 5. And it's 10 spaces between -5 and 5. So my ratio will be 5/10. Favorable outcomes, there's 5 possibilities. Total possible outcomes is 10, and that reduces 10 to 1/2, which is the same thing as the decimal 0.5. 5/10 by definition is 0.5, and 1/2 and 0.5 mean the same thing as 50%, because 1/2 is the same thing as 50 out of 100, which is 50%. Guided practice 3, this is the last one that deals with this same diagram. What is the probability of picking a random point and it landing in the line segment PT out of PQ? Well, let's see, how far apart are P and T from here to here? From -5 to -1, we can see is 4 spaces. To formally work out those 4 spaces, we're going to take the difference between those two numbers, and we'll either subtract -1 minus -5 or -5 minus -1. Either way, when we take the absolute value, will give us 4, and the total possible outcomes for where that point could land is the same as our other problems, 10, because there are 10 spaces between 5 and -5. So 4 out of 10 would be the probability for picking a point on PT if we are going to be choosing out of any of the points on line segment PQ. 4/10 reduces down to 2/5. 4/10 by definition is 0.4. And 0.4 is the same thing as 0.40, which is the same thing as the percent, 40%. So again, we were asked to report our probabilities on guided practice 1, 2, 3 in all 3 forms, fraction, decimal, and percent. So that's why we're showing all 3 of those forms. Example 3. This is going to take us into the probability using areas. So example 3, I've got this target. Someone's doing some target practice. And the question is, what is the probability that the arrow shot lands in the red circle area if the arrow definitely lands somewhere on the target? So the arrow is going to land somewhere in either the gray, the white, or the red areas. So we're going to shoot that arrow. It's going to land someplace on the target. What is the probability that it actually lands in this red circle area? Well, we were told in this problem that the diameter of this large circle is 80 centimeters, and the red circle has a diameter of 16. That means that the full big circle here would have a radius of 40. That's going to be important in a minute. And the red circle will have a radius of 8. So remember, the radius is always half of the diameter. So half of 80 is 40, half of 16 is 8. All right, to figure out what the probability is of that arrow landing in that red circle, if it could land equally in any place on that target, because the person isn't very good at shooting that arrow yet. So if it's just going to randomly fall someplace on that target, The area of the red circle would be the favorable outcomes, and the area of the red circle will be pi times the radius, 8 squared. Remember, the radius is half the diameter here, so half of 16 is 8, over the total possible outcomes, which is the area of this entire large circle. So that is pi times 40 squared, because the radius is 40. That's half of that diameter, 80. And we're going to notice right away the pi's cancel out. So that leaves us with 8 squared, which I can write as 8 times 8 over 40 times 40. I'm going to divide by 8 twice. That will cancel out this 8 and this 8, and 40 divided by 8 is 5. 40 divided by 8 is 5. And that's going to give me 1 times 1 over 5 times 5, and that's equal to 1 over 25. So randomly, that arrow could land in that red circle only 1 out of 25 chances. That's if the skill level of the person shooting the arrow isn't honed or good yet, and they can randomly hit that target somewhere. All right. Example 4 talks about a dog who's in a park. He's dropped a ball someplace in the park. So all of this is the park. And so the question is, what is the probability that the ball is somewhere in the field? So I've marked off the field here, which when you count the squares, you'll find there are 30 squares that make up the field. The question is, if that ball is randomly placed somewhere in that park, because the dog just sort of let it drop out of its mouth and no one really knows where in the park, but someplace, we would have to know not only what is the number of squares for the field, 30, but what are the total number of squares in the park. Unfortunately, the park is not in a rectangle, and we're going to have some squares that are only partial. So what we do to figure out the total area of the park, since we need to know the area of the field over the area of the park, what we do is we count all the field, 30, plus all the squares that we can see that are complete. And we can see there's 52 complete squares. That's 30 plus 8, 38, plus 14 more, which will get you up to 52 full squares. And then we count the partial squares, kind of piece them together. When we do that, we'll get about 6.5 partial squares. Your answer might be a little bit different in counting them, but somewhere around 6.5 when you piece them together. That means altogether in the park there would be about 58.5 total squares in the park area total. All right, so the area of the field would be 30 over about 58.5. If you got 58, 59, somewhere in that area, even 60, you would be fairly close. And again, this is just an approximation. So working, though, with 58.5 as our approximation for the total number of squares in the entire park, what we would do to simplify this, first I'd multiply by 10 over 10 to get rid of the decimal point. That would give me 300 over 585. Then I divide by 5 over 5, since I notice both 300 and 585 are divisible by 5. That would give me 60 over 117. I notice that both 60 and 17 are divisible by 3, so I divide by 3 over 3, and that gives me my fully reduced fraction, 20 over 39. So it looks like there's a little more than half of a chance that that ball will actually be in the field. Just a little more over 1/2. All right, so that concludes all of our guided practice problems for this particular lesson. So now it's time for you to move on into the homework portion, making sure this is recorded on your paper and used as a reference when you are completing your homework. We'll see you next time.